Breaking waves are extremely complex, with billions of variables and molecules all influencing each other. They seem completely unpredictable, or at least we'd need insanely long equations to map them, right? But with modern mathematics, we can calculate, model, and even predict these complex phenomena with remarkable simplicity. This field is known as catastrophe theory. It was invented in the 1960s by the French mathematician René Thom and popularized by Christopher Zeeman in the following decade. Catastrophe theory models phenomena where continuous inputs have discontinuous outputs. In other words, it's the straw that broke the camel's back. These subtle but abrupt transitions can be seen everywhere in life. Like the fight or flight response in a dog, or when prison mates suddenly riot, when two countries go to war, the advent of a global pandemic, a stock market crash, or even when one of us falls asleep or wakes up. It's that one neuron firing that sparks function in the entire brain, which allows the body to go from waking to sleeping. When and why this transition occurs might seem arbitrary from the surface, but we can explain it with a single picture that anyone could understand. But how does this actually work? First, we need to learn about derivatives. A derivative is a method of visualizing the rate of change of a function. It measures the slope of that function at every point. This way, the x-intercepts of the derivative are where the original function was flat or had a slope of 0. First, we must look at the family of functions that describes the manifold or surface of the thing we are trying to model. I will be explaining the cusp, but know that there are others which describe different kinds of catastrophes. To turn the function into the cusp manifold, we take the derivative for each function in the family of functions, and then map only the zeros. This way, we are only mapping the parts of the original function where the slope was 0. There will only be 1, 2, or 3 for each function. When we map all of these points for the entire family of functions, we get the cusp. Each point on the cusp is a possible state the phenomena could be in. These lines on the cusp show where the critical points are. When measuring our phenomena, if we reach this point in state space, we know we are in an unstable region, and any slight move will cause a sudden jump in what we are measuring. This highlighted portion of the cusp is completely unstable, and therefore we will never measure our phenomena to be in this region for more than a few moments. How can we use this quantitatively to solve the world's problems in a meaningful way? How can we apply this to climate change? Small incremental increases in temperature to a sudden catastrophic rise that could wipe out most life on Earth. Catastrophe theory provides such a simple way to visualize these often unintuitive phenomena. So simple, it's almost like poetry.